Is your microphone all set up and going? Okay, okay. Okay, if I could have everyone's attention, we can get started. So my name is Don Siegel. I'm a Max advisor in the mechanical engineering department. So it's my pleasure to introduce Max. Max is my first PhD student to graduate, and so I'm quite excited about that. And he's done it in a pretty quick period of time. So he joined the group back in the summer of 2010, and so has been doing research only for about 4 years, but has been really productive in that period of time. So he's been working on a problem, as you'll hear in a moment, that I think is a great problem because it has these nice fundamental questions, and if we can answer those questions, maybe there's some application payoff at the end of the tunnel. So as Max will tell you, he's working on metal-air, lithium-oxygen batteries, or lithium-air batteries. There's lots of different names used for these batteries. And they're a speculative technology. They have lots of promise, potentially really high specific energy, so energies by mass, but they have lots of challenges. So these aren't commercial technologies yet. And there's some fundamental questions, like I said, if we could sort them out, that might push them off of the lab bench and into a car, hopefully. So what's unusual about these batteries is that as they discharge, they nucleate a new phase, which could be a really good resistor and could prevent charge transport, which you need to have happen as quickly, as efficiently as possible to make for a good battery. So if you discharge these batteries slowly, or if you're careful, there's some tricks which we don't quite understand that allow these systems in the lab to get to high capacities. But if you discharge quickly, there are some cases where the batteries die an early death, maybe due to transport limitations. So trying to understand how moving electrons, moving charge through these nucleating and growing discharge phases with complications associated with microstructure and maybe different composition has been Max's focus. So he's been starting, well, he has started with approaching this from the atomic scale or the electronic structure level, trying to understand how ground state electron properties influence transport, but more recently has started a collaboration with Chuck Monroe, who's on the committee, to extend some of that atomic scale input to continuum models to allow them to make a more macro scale prediction of how potential and charge gradients occur or influence performance in these systems. So it's really a nice multi-scale study, I'd say. And coming back to the productivity, so Max, like I said, has been really productive. He's already got 5 papers which have been published. He's got a proceedings paper. He's got another paper that's been submitted to Jackson, is under review. There's 2 more papers which I've seen drafts of, which should go out in a month or so. One of them is an invited review article for a book. And then there's some other work Max has been doing with some collaborators at Lawrence Livermore. He went there for the Computational Material Science Summer Institute a couple of years ago and has started working with some of those guys, or continues to collaborate with some of his mentors back there. So by my count, that's about 10 or more papers that will come out of Max's dissertation once he's published everything that he started. And I think in total he's got over 100 citations for some of the work which has already been out there in a very short period of time. So Max has done really well, and he tells me he's going to be streaming this presentation to YouTube, so we might get some questions from the chat room. I'm going to moderate that, and in the Q&A later maybe we'll come back to some of those. But so with that, I'll turn things over to Max.
All right, thank you for that introduction, Don. So I'd like to start off by just giving sort of a broad overview of everything I've been doing in the last 4 or 5 years. What I'm going to be talking about today is mostly these first 5 items on the list here, dealing with lithium-oxygen batteries and transport in lithium-oxygen batteries. But I also had the chance to work on a few other projects, including a collaboration with Lawrence Livermore National Laboratory looking at solid-liquid interfaces, a little bit of work on lithium insertion electrodes, as well as, like Don mentioned, a project through a summer internship at Lawrence Livermore looking at electrochemical double-layer capacitors, and also a little bit of work on reductive stability of lithium-ion solvents. But I'm not going to be talking about those today. Instead, I'm going to be focusing on lithium-oxygen batteries. And to put that in context, I think as many of you probably know, right now society is in a position where we're beginning to transition from an energy economy that's based on fossil fuels to one that's based on energy sources which are renewable, efficient, and sustainable. And so the Germans have a word for this, Energiewende, which can be translated as energy transition. And so right now there's a very high level of interest, both in the US and outside the US, in developing technologies which will enable the energy transition. One of the specific technologies that's expected to play a big role in any energy transition is electric vehicles. And so for that reason, there's been a lot of interest in developing new technologies to enable electric vehicles. And so one example of that is this EV Everywhere grand challenge developed by the Department of Energy last year. And so one of the key technologies which they identified was the battery. And in particular, they set targets for the next 10 years to reduce the cost, the size, and the weight of batteries. And of course, the reason for this is that the cost of the batteries has a big impact on the cost of an electric car. And the size and the weight of the battery has a big impact on how far your car can go on one charge, what the range is. And so for that reason, people have started looking now towards new battery chemistries beyond the state-of-the-art, which is lithium-ion batteries used in most electric vehicles today. And so this table is showing some system-level projections for the energy density of a battery pack made from lithium-oxygen batteries. And as you can see, the projected energy per weight and energy per volume for this system is expected to be significantly higher than the system-level energy densities for the state-of-the-art lithium-ion battery packs. So how does a lithium-oxygen battery work? Well, the basic reaction going on is that you have lithium metal in the negative electrode, which combines with oxygen either taken from the atmosphere or an oxygen tank, and they combine to form lithium peroxide. And so lithium peroxide has a very low solubility in the organic solvents which are used in these batteries. And as a result, it precipitates out as a solid, which accumulates on top of the positive electrode, which is typically made out of porous carbon. Then during recharge, the reverse happens, and lithium peroxide decomposes, releasing lithium back to the negative electrode and oxygen back to the atmosphere. And so most of what I'm going to be talking about today is dealing with this discharge product here, Li-2O2, and how electrons and ions can move through it. Because, of course, if you cover the electrode with something that blocks electrons and ions, that's going to severely limit the capabilities of your battery. So there's a number of things that you need in order to have a battery that's suitable for an electric car or any other application. First of all, you need to be able to discharge it and recharge it at a high rate. And so this corresponds to how fast your car could accelerate and how long it would take you to recharge it. You also need to be able to have a high capacity. And as I said before, that corresponds to how many miles you can go on one charge. You also need to be able to run your battery through many cycles, because this is going to determine the lifetime, how many years your battery will last. And finally, you also need to be able to have a high voltaic efficiency, meaning that the amount of energy you get out of your battery when you discharge it had better be close to the amount of energy that you put in when you charge it. And so to illustrate this last issue of voltaic efficiency, here I'm showing some data from a cycle of a lithium-oxygen battery. And so what you're looking at is the voltage in the battery when it's discharged at a fixed current and then recharged at a fixed current. And so if this cell was 100% efficient, then both the discharge and the recharge would occur at this equilibrium voltage shown by this dashed line. Instead, what you see is that recharge occurs at a much higher voltage, which means that when you're charging it, you're putting in a lot more energy than you got out when you discharged it. So with lithium-oxygen batteries, which people are now building and testing in laboratories, people can achieve targets for one or maybe two of these things at a time. But the problem is making a lithium-oxygen battery that can do all four of these things simultaneously. And so there's some interesting and subtle trade-offs in here. For example, when you increase the discharge rate of a lithium-oxygen battery, that can actually increase the voltaic efficiency during recharge. And this might seem counterintuitive, but this can occur because when you increase the discharge rate, that will change the morphology of the discharge product and change its structure. And that, in turn, will affect the efficiency during recharge. So one of the main origins of the trade-offs and limitations in these different aspects of battery performance comes from, like I said, the ability of electrons and ions to move through the discharge product. So here's an SEM image showing the positive electrode from a lithium oxygen cell. And what you're seeing here is lithium peroxide, which is these biconcave discs, which is deposited on top of a porous electrode, made out of porous carbon. And so one of the things I'm going to talk about is how lithium peroxide, as a pure bulk crystal, is a very poor conductor. And this can cause the performance of the battery to become very limited when it covers up the electrode. But as you can see, the actual morphology of the discharge product is pretty complex. You have lots of surfaces, you have grain boundaries in here, you have impurities in here. And so one of the fundamental questions is, well, how can all of these features in the discharge product, how do they affect the transport of electrons and ions? And this is an important question because if you find out that a certain feature can improve the transport properties, then that suggests you want to design your electrode to promote that feature. And that would help you get around some of these performance limitations. So there's 4 specific features in the discharge product I've been looking at in my dissertation. So the first thing I'm going to talk about is structural disorder. And what our calculations found is that lithium-ion transport is actually much faster when you have amorphous lithium peroxide instead of crystalline lithium peroxide. The second thing I'm going to talk about is what happens when you introduce impurities into the discharge product. And what we're going to see is that introducing transition metals into the discharge product can improve charge transport during the recharge of the battery. I'm also going to talk about surfaces, which play a number of important roles. What we're going to find is that the intrinsic conductivity at surfaces is not very different from the bulk lithium peroxide. However, the last item here, which is related to surfaces and interfaces, is what happens when you have a space charge layer near a surface or an interface, so an accumulation of charge carriers. And what we're going to see is that the space charge layer can have a big impact on transport properties. One of the things that makes lithium oxygen batteries a very interesting problem to work on is that it's a very multi-scale problem. So you have processes that are occurring on the femtosecond time scale and the sub-nanometer length scale, like electron transfer and chemical reactions. You also have processes happening on, such as degradation, which happens over time periods of years. And you have, maybe thermal transport in a battery pack, which is a length scale of meters. And so I think a nice analogy for this is like thinking about a colony of ants. If you want to understand how a colony of ants works, well, the first thing you have to do is try to understand how a single ant works. And then once you've figured that out, you have to determine how a whole bunch of ants work, and they're all interacting with each other. And so in this analogy, the ant might represent maybe one atom or molecule, and the colony of ants could represent, say, one particle of lithium peroxide or some component of the electrode. So the basic picture of what I've been doing is to try to develop continuum transport models to understand the transport in the discharge product of a lithium oxygen cell. And so of course, in order to make a continuum transport model, you need to know a couple of things. First of all, you have to know, well, what are the species that are moving? Are they lithium ions, lithium vacancies, electrons, holes? And then you also need some parameters to describe those species, such as diffusion coefficients and mobilities. You also need some boundary conditions, which describe what's going on at the boundaries of the discharge product. And so that's going to be related to the defect concentrations under some equilibrium condition. So these macroscopic parameters, the mobilities and the concentrations of defects under equilibrium, are related to the microscopic quantities, such as the formation energy of a defect, the amount of energy it takes to create a defect, and also the energy barrier for a defect to migrate from one site to the next. And so what I do is to calculate these microscopic quantities from atomistic simulations. So what I'm going to do next is talk about the basic approach for the atomistic simulations in order to calculate these defect formation energies and migration energies. There's two key approximations being made in these simulations. The first is that you treat the nuclei as being fixed classical points, whereas on the other hand, the electrons are treated quantum mechanically. And the reason for this approximation is that, well, the masses of the nuclei are much, much larger than the masses of the electrons, so they can be treated as classical points. The second key approximation is that we assume the electrons stay in their ground state. And so this approximation is motivated by the fact that the energies that we're dealing with here for chemical bonds on the order of 1 electron volt are much larger than the thermal energy associated with thermal excitation. It's about 25 millielectron volts at room temperature. So under these approximations, the energies are determined by the electronic Schrodinger equation. So basically this is showing us that the many-body wave function is an eigenfunction of the Hamiltonian. And so the Hamiltonian includes like, the kinetic energy operator. Basically says that kinetic energy is related to how fast the wave function is oscillating. What I'm calling an external potential, which represents the interactions between the electrons and the nuclei. And then, of course, there's the electron-electron interactions. Now, the problem with this equation from a numerical point of view is that it's extremely difficult to solve because this many-body wave function has too many degrees of freedom. So if I have n electrons, then this wave function is a function of 3n variables because I have 3 spatial dimensions. And so even if I have a modest number of electrons, even storing this wave function on a computer becomes very quickly becomes impossible because its size grows exponentially with the number of electrons. So in order to get a more tractable approach on solving the electronic structure problem, we use density functional theory. So the idea here is that the system I'm interested in is a bunch of electrons which are all interacting with each other. They're sitting inside some sort of potential well. I can map this onto a system of electrons which are not interacting with each other, and instead are sitting in an effective potential which in some way includes the effects of the electron-electron interaction. So mathematically, in Kohn-Sham density functional theory, this is represented by the Kohn-Sham equation, which describes the wave functions for these fictitious non-interacting electrons. And so it looks very similar to the Schrodinger equation, except that this electron-electron interaction term has been replaced with this effective potential. And now, instead of dealing with a many-body wave function, which is a function of 3n variables, I now need to find single particle wave functions for each of my electrons. So now I have n functions of 3 variables. And so this is, from a numerical point of view, much more tractable. Now there's some subtlety here in that in the Kohn-Sham equation, this effective potential, well, you have to know what it is, and it's, in the Kohn-Sham formalism, a functional of the electron density. And so there's a self-consistency problem here, right, because the wave functions are determined by the Hamiltonian, but of course the Hamiltonian depends on the charge density, which depends on the wave functions. So you have to solve this in a self-consistent manner. Now really the thing that's magical about density functional theory and what Walter Kohn won the Nobel Prize for is showing that there is some density functional, some mapping between the electron density n and the effective potential v, such that for any external potential you have, the solution to this equation will give you the exact same electron density and exact same ground state energy as the Schrodinger equation. Now, of course, just because you can prove that such a functional exists doesn't mean you know what it is. And so the challenge there is coming up with good approximations for what this effective potential is. So in my calculations, I use what's called the HSE, exchange correlation functional. So here the effective potential is represented as two terms. First, there's a heart rate potential, which represents the classical electrostatic energy associated with the charge density. And then there's this exchange correlation potential, which is, well, everything else, the interaction. And so in the HSE functional, this exchange correlation potential is further divided into two different parts. First, you have exact exchange contribution, and then you have PDE, generalized gradient contribution. I'm not going to go, in the interest of time, into great detail about what exactly that means. But one of the important points is that because we're mixing these two different contributions to exchange and correlation, there's a free parameter in this functional, which is in what ratio do you mix them. And so the amount of exact exchange which I mix, I've determined by fitting the fundamental band gap of lithium peroxide to the band gap calculated by many-body perturbation theory method. And so, again, in the interest of time, I'm not going to go into details about how exactly that works. Most of the simulations here are using a few hundred atoms, and all of the calculations on atomistic systems have been done using the Vienna ab initio software package. So now that we have a way to calculate the energies of electrons and ions, so how does this relate to the macroscopic quantities that we're interested in? So defect, concentrations, and mobilities. So of course, creating a defect in the solid always takes energy, but because it creates entropy, there will be some concentration of defects at equilibrium. That concentration can be expressed in terms of a Boltzmann distribution, which depends on the formation energy, which is the amount of energy it takes to create one of the defects. This equation here is showing how we calculate those defect formation energies from density functional theory. So essentially what we do is we do a calculation on a big simulation cell with a defect in it, and then we subtract from that the energy of a big cell without any defects in it. And now, of course, since we're adding or removing electrons, we're adding or removing atoms, we need to account for the chemical potentials of those species. In other words, what the reservoir for lithium, oxygen, and electrons is. And that's accounted for by these chemical potential terms here. Lastly, there's also a finite size correction we include, which is in order to try to extrapolate in order to the limit where the defects are very dilute and not interacting with each other. So now the chemical potential of electrons, which is at the Fermi level, in principle in a solid, be anywhere between the valence band and the conduction band. If you're talking about a bulk material, in general, the Fermi level will be fixed by electron neutrality, which says that the concentration of positive charges and negative charges has to balance out. And that's expressed mathematically here. Now, at the end of my talk, I'm going to come back and consider the regimes where this equation does not hold. So if you're talking about a deposit which is very small, electron neutrality may not be satisfied. And I'm going to come back to what the consequences of that can be. So these calculations here are at zero temperature. The temperature enters in the configurational entropy in terms of different sites for defects, which is in this Boltzmann factor here. So we're ignoring basically the vibrational contributions to free energy. So the first thing I'm going to talk about now is charge transport in the bulk crystal. And so the first question there is, well, what are the charge carriers in bulk lithium peroxide? So we considered 23 possible different defects. This includes vacancies and interstitials, which is where you either remove an atom or add in an extra atom, as well as hole and electron polarons. And so this is where you add or remove an electron, which is taken from one of these oxygen dimers here. And so one of the things that makes lithium peroxide a very interesting material is the fact that, unlike other oxides, it has these covalently bonded oxygen dimers. And one of the consequences of this, which we're going to see, is that this gives the oxygen dimers the ability to give up an electron rather easily. And so we have here a material where one of the species can change its charge state. And so that's illustrated in this cartoon here. So In the defect-free crystal, all of the oxygen dimers each have 2 electrons, which have been donated by the lithium. But sometimes the oxygen dimers will be willing to give up one of those electrons. And so one of the themes that's emerged for lithium-oxygen batteries is that the ability of these oxygen dimers to change their charge state is a driving force behind a lot of the phenomenon which you see. This graph is showing the calculated formation energies for the lowest of those 23 defects in lithium peroxide. So here I'm plotting the formation energy of those defects as a function of the Fermi level, which in principle rate can be anywhere between the valence band and the conduction band. This vertical dashed line is showing where the electroneutrality condition is satisfied. So in other words, where the positive and negative charges balance out. So I like to think of this as sort of a supply and demand picture. So the Fermi level sort of represents the price of electrons in terms of energy, and the formation energy, which is related to the concentration, represents the supply or demand. And of course, when supply and demand are equal, which is where these lines cross, you have equilibrium. And so what you can see from this graph is that the defects with the lowest formation energy, and therefore the highest equilibrium concentration, will be these negative lithium vacancies, which is where you take out a lithium plus ion, and these hole polarons, which is where you take out an electron from one of these oxygen dimers. So the second thing we need to know, besides the concentrations of defects, is what their mobilities are. And so we can calculate that by looking at the energy for the defect to migrate from one site to the next. And so that's being shown here for the hopping of a polaron, which corresponds to the tunneling of an electron from one site to the next. So here you're looking at the energy as a whole polaron hops from one site to an adjacent site. That's shown in this video here. And so the yellow surfaces are showing you where the magnetization density is. And so the magnetization density is associated with the electron in the whole polaron that's unpaired, because now you've taken away the electron which it normally would be paired with. And so what you can see is that as the polaron hops back and forth between these two sites, the magnetization density moves, and also the ions around it will be perturbed in order to accommodate the extra electron. So now by combining these equilibrium concentrations and the migration barriers, we can estimate what the conductivity is. And so our calculations show that the intrinsic conductivity of crystalline lithium peroxide is very low. And the reason for this essentially is that the equilibrium concentration of defects is very small. And so as a result, the conductivity is very low, especially compared to other battery materials like lithium iron phosphate or carbon black. And so it suggests that having lithium peroxide accumulate in your electrode is going to be a problem for a lithium oxygen battery. So just wanted to comment on, there's been a couple experiments that have tried to measure the conductivity of lithium peroxide or the discharge product in a lithium oxygen battery. And the conductivities they measured were also quite low. However, they were significantly higher than those predicted by our simulations. And that's a result that is maybe not too surprising, because the thing that's being measured in our calculations is not really the same thing that we measured in the experiment. So in our calculations, right, we're looking at a pure, perfect crystal. But of course, the thing that you have in these experiments is actually something that's much more complex, with grain boundaries and impurities and other complications. And in particular, because the intrinsic defect concentration is so low, what you see in an experiment is likely going to be dominated by whatever impurities are there. And so the effect of impurities is something I'm going to come back to later. So what I'm going to talk about next is the effect of structural disorder. The motivation for this comes from the fact that there's been sort of a growing trend in experiments on lithium oxygen batteries to see not crystalline lithium peroxide, but amorphous lithium peroxide, or nanocrystalline lithium peroxide. And this is particularly interesting because a number of those experiments have suggested that when the discharge product is amorphous, then it's actually easier to recharge than when it's crystalline. And so that's shown here in these discharge and recharge curves. And so what you can see is that in this particular case, the authors modified their electrode in such a way that they believed increased the number of amorphous grain boundaries. And when they did that, the charging potential went down quite a bit from about 4 volts to about 3¼ volts. And so this raises the question, well, so what's the difference between the crystalline and amorphous lithium peroxide? So in order to answer this, the first thing to do, of course, is to generate a model for amorphous lithium peroxide. And so we did that using melt and quench molecular dynamics. So we start out with a crystal, and we start running molecular dynamics and gradually increase the temperature until eventually that crystal will melt. And what you'll see is that these distinct layers of oxygen will merge together once the material is melted. And then after it melts, we bring the temperature back down again in order to quench it and create a model for amorphous lithium peroxide. Now, one of the challenges, of course, with making a model for an amorphous solid is that, well, molecular dynamics is path dependent, and so what you get at the end, well, depends on the temperature and the process in the middle. And in particular, one of the implications of this for our system is that if you don't constrain these oxygen-oxygen bonds, then when you go through high temperatures, those bonds will break. And then when you quench the system, you'll be left with a bunch of broken bonds, which is probably not a very realistic model for the lithium-oxygen discharge product. So what we did in order to address this problem is to constrain the oxygen-oxygen bonds to be a fixed distance during the high temperature parts of the melt and quench process, and then release those constraints when it's back to a low temperature. In terms of the bulk properties, the crystalline and amorphous phases we find to actually be very similar. So if you look at the density, there's a slight decrease. The band gap is essentially the same. And the equilibrium potential, which is related to the formation energy, is a little bit lower. This graph here is showing the radial distribution functions for the crystalline and amorphous phases, which basically is showing a histogram of the distances between atoms. And so what you can see is that the lithium-lithium, lithium-oxygen, and oxygen-oxygen distances are essentially the same in both the crystalline and amorphous phases. Now, the fact that these two systems are very similar is maybe not too much of a surprise because bonding between the lithium and oxygen is primarily electrostatic, which means that it's going to be very isotropic and not depend on which way things are oriented. So the implications of these differences is that there'll be a slight decrease in the volumetric and gravimetric energy density of a battery based on the amorphous phase because the volume is a little bit bigger and the equilibrium potential is a little bit lower. However, this might be worth it if the transport properties were significantly different. And so in order to look at those transport properties, we studied the defect chemistry of the amorphous phase. Now, defects in an amorphous solid are different from defects in a crystalline solid in that now every site is unique and will have a different formation energy. And so that's what we're showing here is that the formation energies for lithium vacancies and the whole polarons vary between different sites. So in order to try to get a handle on this, we tried to get a statistical sampling of the different sites inside of the amorphous model. So here you're seeing the path in yellow that we considered for lithium vacancy migration across our amorphous model. So this path is not intended to represent the path that an actual lithium vacancy would take. Rather, it's just there to get a sampling which will be statistically representative of all the different sites and barriers in the system. And so here you can see the energy profile for a lithium vacancy to move across this path. So here the thick lines are showing the amount of energy to create a vacancy at those different sites. And then, of course, there's an energy barrier in order to go from one site to the next. So as you can see, there's a fairly wide range in the energy barriers and formation energies. And so what we want to do is, well, so given this range of values, all of these different sites, we want to extract a macroscopic quantity, the conductivity. And so in order to do that, we borrowed some ideas from percolation theory. And so it's been observed that amorphous solids will often exhibit an Arrhenius type dependence of conductivity on temperature, where there's some activation energy which characterizes the conductivity. And so the question is, well, what is the energy scale for lithium diffusion in this system?
This one must be to some extent a possible transport might be variable nature in the amorphous space.
You mean where the sites have a different distance between each other?
So lithium tunnels, and the tunnel they have to have a very similar energy. When you do the thing is at lower temperatures, they end up coming farther. There's a functional form which is not that.
Oh, I see what you're saying.
Very different function. So that is also a likely way to look in the amorphous space.
Yeah, so here we're assuming that the lithium ions, the nuclei, are to be treated classically. So you're saying that there could also be a mechanism where they tunnel quantum mechanically?
Are there experiments which look at the temperature conductivity?
Of amorphous solids?
Yes, amorphous.
So I haven't seen anybody do a measurement on amorphous lithium peroxide of conductivity versus temperature. So people have tried that for powders of the crystal. Yeah. Yeah, one of the challenges I think is it's hard to get an apples-to-apples comparison because you need to be able to synthesize both a high purity crystal and a high purity amorphous material. But yeah, anyway, yeah. So we haven't included any possible effects of lithium tunneling. But what we're going to see is that even not accounting for that mechanism, the conductivity here is predicted to be much higher than in the crystalline phase. Really higher. Even, right, yeah. Yeah, certainly could be. So at any rate, to estimate the conductivity here and estimate the activation energy, what we look at is the 20th percentile of the transition states. And so the idea here is that if you're a lithium vacancy wandering around through the structure, you don't need to be able to cross over every single barrier. You certainly don't need to be able to cross over the highest energy ones. You just need to be able to cross over a large enough fraction so that when you go to a new site, there'll be at least one other barrier which you can cross over. That way you can have long-range transport. And so that motivates the idea that the activation energy will be determined not by the highest barrier or the lowest barrier, but rather by something in between. And so this 20% number represents our estimate of the bond percolation threshold for the network formed by the lithium sites in the structure. So the upshot of all this is that from our microscopic model of the amorphous phase, we can estimate the macroscopic quantity, the conductivity, associated with the ions and the electrons. And so what you see here is that In the amorphous phase, the ionic conductivity is predicted to be much higher than in the crystalline phase. In terms of the electronic conductivity associated with polar ions, there's also an increase, although it's not as dramatic. But so our speculation is that the improvements in the transport property of the amorphous phase could make the amorphous lithium peroxide a more desirable discharge product, because then it might be easier to recharge in a lithium-oxygen battery. And so it suggests that you might want to design your electrode in such a way to promote the formation of amorphous lithium peroxide. So next thing I'm going to talk about is what happens when impurities are introduced into the discharge product. So this idea has been motivated by, well, actually there's been a growing number of experiments where people take a lithium-oxygen electrode and they start adding in new materials into it. So, for example, adding in cobalt oxide. And what they see is that when they add in new materials, sometimes the charging potentials will go down, meaning that you have a more efficient cell. And so that's illustrated here, where you can see that when they added cobalt oxide into this cell, the charging potential went down by 400 millivolts. And so the mechanism behind this is really not well understood. There have been a number of different hypotheses have been suggested, but the one that we wanted to consider is, well, what would happen if some of the cobalt ions or metal ions from these additions got incorporated inside of the discharge product? So in order to probe that, what we did is to calculate the formation energies for cobalt substitutions in lithium peroxide. So here we're replacing a lithium ion, lithium plus ion, with a cobalt 2 plus or a cobalt 3 plus ion. And then we also considered possibilities where the cobalt substitution could be bound to a lithium ion vacancy. So you have a cobalt substitution at one site and a lithium vacancy at an adjacent site. And so what this graph is showing is the formation energies for the lowest energy substitutions. And what you can see is that the presence of the cobalt substitutions has a pretty big impact on the defect chemistry. And that's because these cobalt substitutions have a lower formation energy than the whole polar ions. And as a result, the Fermi level shifts to higher energies, and the formation energies of lithium vacancies goes down, and the formation energies of whole polar ions goes up. So given that the introduction of an impurity can have a big effect on the defect chemistry, the natural question asked is, well, how will this affect transport in a lithium-oxygen cell? And so what we wanted to do in order to try to get a accurate understanding of that is to develop a continuum transport model to account for all of these different species which we have that are moving around. So our model represents a 1D film of lithium peroxide that's growing on top of the electrode. And we considered two different possible mechanisms which have been suggested in the literature for how discharge or recharge might occur. The first scenario, which I'm calling scenario 1, represents layer by layer deposition or stripping. So in this case, lithium peroxide decomposes at the interface with the electrolyte during recharge and releases lithium and oxygen back to the electrolyte. And electrons have to travel through the peroxide film from the electrode to the electrolyte. Well, actually, electrons move the other direction. Polar ions move from the electrode to the electrolyte. And the same process can happen in reverse during discharge, in which case the polar ions move from the electrolyte to the electrode. Now, the second mechanism, which we also considered, is one which was suggested recently by some computational work, in which you have two-phase delithiation process. So in this scenario, what you would have is that at the buried interface between the lithium peroxide and the electrode, you take out lithium atoms from there, you could, in principle, nucleate a new phase, which is deficient in lithium. And so you would, during recharge, gradually convert this lithium peroxide deposit into some lithium deficient phase. And then once it all had been converted, presumably this lithium deficient phase could dissolve or be electrochemically oxidized. So the two key differences between these scenarios are that, first of all, in scenario 1, the charge transport through the peroxide is mediated by electrons, whereas in scenario 2, it's mediated by ions. The second difference is that Scenario 1 represents something which could happen in principle as a discharge or a recharge mechanism, whereas scenario 2 represents something which only can happen during recharge. So these are the equations that we use to model this system. And so the most fundamental equations on here represent the conservation of mass and conservation of charge. So that's these three equations in the bottom here, which tell you that the fluxes of cobalt ions, lithium ions, and the current must be divergence-free. And so the fluxes of all the different species, we have polarons, vacancies, cobalt substitutions, and cobalt substitution vacancy bound pairs are given by Nernst-Planck flux laws, which basically say that the flux of any species is driven by two things. First of all, a concentration gradient, and second of all, an electric field. And so the connection between this continuum model and our microscopic atomistic models comes in two places. First of all, these diffusion coefficients, which describe how fast the different species move. We take those from our density functional theory calculations. And then second of all, the boundary conditions, which represent the concentrations of these defects when they're in equilibrium, are taken from the DFT calculations, which I showed previously. So what this model predicts is that lithium peroxide, when it's doped, acts essentially like a diode. Transport is fast during recharge, but slow during discharge. And so this is the case regardless of whether you're talking about scenario 1, layer by layer deposition and stripping, or scenario 2, we have this two-phase delithiation. And so what this model predicts is that when you're under typical recharge conditions for a lithium-oxygen battery, meaning currents of about 1 microamp per square centimeter and a deposit thickness of about 100 nanometers, then you only need a potential drop of a few millivolts in order to drive those currents. And so our speculation is that this mechanism could explain why lithium-oxygen batteries, which have cobalt oxide or other transition metal compounds in them, can be recharged more easily than without those materials. So I'm going to move on now to talk about lithium peroxide surfaces. And so the surfaces play a number of different important roles in lithium-oxygen batteries. So one of them is the fact that surfaces are very important for the precipitation and growth of the discharge product. They also could play an important role in charge transport in terms of charge carriers at the surfaces as well as phase charge layers near the surfaces. And also, something which I'm not going to talk about today is electrolyte degradation. We have chemical reactions, undesirable chemical reactions between lithium peroxide and the liquid electrolyte. The first question that we need to answer is, well, what are the surfaces of lithium peroxide? And so what we did is to look at 3 different Miller indices and try a bunch of different possible terminations in order to find the ones which have the lowest surface energy. And of course, the idea is that the surfaces which take the least energy to create will be the ones which you expect to see in the deposit. And so here I'm showing in bold the surfaces, the lowest energy surfaces for each Miller index that we've calculated. And so based on these energies, we can predict what the shape of a lithium peroxide crystallite would be using Wolff's construction, which basically says that the equilibrium shape of a crystallite will be determined by the rule that the distance from the center of the crystallite to the center of each facet will be proportional to the surface energy for that facet. And so this is the equilibrium crystallite shape we get, which has 2 surfaces. This is 0, 0, 0, 1 stoichiometric surface and a 1, 1 bar, 0, 0 stoichiometric surface. Or there should be a bar over that 1. So one of the things is that the shape that's predicted here is very different from the shape that's seen in the experiments in lithium-oxygen batteries. So the crystallite shape in lithium-oxygen batteries is the sort of flat pancake shapes, which is a very different aspect ratio than the sort of soup pan shape that's predicted by our calculations. And so what this suggests is that the crystallites which are growing in the battery, their shape is not determined by thermodynamic equilibrium. Instead, it's determined by some kinetic factor. So for example, maybe the attachment of lithium peroxide along sides of the crystallite here is much faster than on the top. Yeah. Well, so from the electron diffraction pattern here, you can see that there is some crystallinity. This experiment, I don't think they did any TEM, but there are other experiments where people have done TEM, and in fact, you can see that in here. And so in TEM, sometimes people have seen crystalline phases, sometimes they've also seen amorphous phases. Yeah, so there's a lot of challenges. Right, it reacts with water and CO2 fairly quickly. Beam damage is also a problem. Okay, so the next thing we looked at was defect chemistry on surfaces, which I'm just going to touch on briefly. And what we found is that when looking at polarons and vacancies on lithium peroxide surfaces, that the formation energies of polarons is pretty similar to the bulk lithium peroxide. We also looked at the migration barriers. So here I'm just showing for the 0001 surface, different polaron migration pathways that we looked at. What we found is that the barriers for polaron hopping at surfaces is also pretty similar to bulk lithium peroxide, which suggests that the intrinsic conductivity of the surfaces may not be very different from the bulk lithium peroxide. But this leads me to the last topic which I'm going to talk about, which is space charge effects, is the accumulation of excess charge carriers near surfaces and interfaces. So this is motivated by looking at the energy levels of different components in a lithium oxygen battery. So here on the left, you're looking at the energy levels in lithium peroxide. So you're looking at the valence band maximum, the whole polaron energy level, and the intrinsic Fermi level relative to vacuum. Now, of course, the positions of these levels relative to vacuum depends on which surface termination your material has. But when you compare these to the Fermi levels of other common electrode materials, such as carbon, gold, or platinum, what you see is that the Fermi level of the lithium peroxide surfaces, which we found to be on the equilibrium crystallite shape, so the 0001 and the 1 bar 00, the Fermi levels are much higher than the Fermi levels of these other electrode materials. And so what this suggests is that if you put lithium peroxide into contact with carbon, that electrons would like to lower their energy by leaving lithium peroxide and going into the carbon. Similarly, if you look at the position of the lithium oxygen redox potential, it's also below the Fermi levels for these surfaces, or the Fermi levels of lithium peroxide with these terminations. And so what you would expect is to form a space charge layer, which is illustrated here. So if you have lithium peroxide, electrons would exchange with the electrode, and you'd have a double layer with electrons in the electrode and full polarons in lithium peroxide. And so, of course, the question that we're interested in is, well, if your lithium peroxide deposit is thin enough so that it's comparable to the thickness of the space charge layer, how is that going to affect transport in your battery? And so the conceptual model we made to try to understand this is considering, again, just a one-dimensional lithium peroxide film. And here we allow whole polarons to diffuse in the film and assume that electron exchange with the electrode is in equilibrium, and that the lithium-oxygen redox couple is in the equilibrium at the interface with the electrolyte. And so mathematically, we model this with this set of equations. So the most fundamental equation here is, again, conservation of charge, which tells us the current is divergence-free. The electrostatic potential in this film is given by Poisson's equation, which relates to the charge density associated with these excess hole polarons. And so the relationship between this model and the microscopic picture, it comes in a couple places. One is these diffusion coefficients for hole polarons, and a second is in the dielectric constant, which enters into Poisson's equation, determines basically the amount of screening between charges. So what we can do is compare this to some experiments, which are done not on porous electrodes, but instead on flat electrodes, where you're growing essentially a compact film of lithium peroxide. And so this is showing some experimental data where lithium peroxide is being deposited. And what you see is that at the beginning of deposition, the potential is at a plateau or slowly decreasing. But then when the film starts to get thick, and so this corresponds to about 4 nanometers, then the potential suddenly drops. And so this was attributed to the passivation of the electrode by this film. Now, it's been assumed in the past that this effect was that all of the charge transport going on here through this film was due to electron tunneling. But what we found is that by applying our model to this situation and fitting the parameters to reproduce these curves, we actually see that this same sudden death behavior, where you see a dramatic decrease in the potential, can be explained by the diffusion of hole polarons in the space charge layer. And so essentially what's going on here is that as your film gets thicker than the thickness of that space charge layer, you don't have very many hole polarons, and so charge transport becomes very slow, and potential rapidly drops. So I want to just step back and summarize, everything that basically we found from all of this. So the first thing we found is that bulk lithium peroxide is not a very good conductor. The transport is mediated by lithium-ion vacancies and hole polarons, but because their equilibrium concentration is so low, the conductivity is not very high. And I should also mention that at about the same time that we published this work, there was an experimental study that came to the same conclusion regarding the identities of the charge carriers based on measuring the conductivity as a function of oxygen pressure and EPR measurements. They also concluded that lithium-ion vacancies and hole polarons were the charge carriers. The second important thing we found is that structural disorder in the discharge product improves the lithium-ion transport. Similarly, impurities can alter the defect chemistry, and we predict that that can improve transport during recharge of the battery. The defect chemistry at lithium peroxide surfaces seems to be fairly similar to what you see in the bulk lithium peroxide. However, near the surfaces where a space charge layer might form, there can be a big improvement in electron transport because you have a higher concentration of hole polarons. So I want to conclude by speculating on, well, given these results, what would they suggest about battery design? So the first thing that these results suggest is that you would want to promote the formation of amorphous lithium peroxide because it has better transport properties, and so it would be easier to recharge. Similarly, you would want your discharge product to be impure and doped with transition metals or some other sort of cation. Another interesting possibility, which is suggested by our calculations, is that the orientation of the crystallites in the discharge product would be important. And the reason for this is that the diffusion coefficients and the dielectric tensors are anisotropic. And so if you orient your crystal to be in the direction in which charge transport is faster or the space charge layer is thicker, that could give you better performance. And then finally, you would want to operate your battery at a higher temperature. This is because the diffusion coefficients for these defect migration are thermally activated. This will be greatly increased at higher temperature. So I'd like to thank the sponsors who made all this work possible: the Bosch Corporation, Department of Energy, U.S.-China Clean Vehicles Consortium, and the Joint Center for Energy Storage Research. And with that, I'd be happy to answer any questions you might have.
Okay, thanks, Max. So this is my first time doing this, so I'm a little unsure of the procedure. But my understanding is we now have questions from the entire audience, and then follow up with the committee, and then Max will do that at the very end. So let's open it up to the floor.
Brandon, I think.
How realistic is it that defects in a real
So that's a good question, and so Chris Vanderwall actually asked me the same question. And so at long distances, the main form of interaction between these defects would be the electrostatic interaction. And so in all of my calculations, I've been ignoring those interactions because the concentrations I'm dealing with are on the order of 1 part per million, which I'm assuming is dilute enough in order to neglect those electrostatic interactions between defects. But what you would expect is if there were interactions, the defects would exert, you have positive defects moving this way and negative ones moving this way, they would exert some drag on each other. Yeah, Mark?
At one point, you did this melting and constrain oxygen. Do you think doing that constraining modifies the time? Does that constraining effect that you end up with? That important?
So the question is, how does the constraint on the oxygen bonds affect the final structure you end up with? So it certainly does, right? So if you don't do any constraints, then you end up in a structure where instead of having oxygen atoms that are covalently bonded to each other, they'll be broken apart. And that situation with the broken bonds is something which, from experiments that have done isotopic labeling, I think is unrealistic, at least in the context of a lithium-oxygen battery. So certainly there's one big difference in that whether or not you end up with the oxygen atoms being bonded to each other. Right, yeah, so in the case of temperature, there have been a few experiments where they did basically try running cells at higher temperatures. So what they found in those experiments is that generally the charging potentials went down, which is what you would expect.
That's consistent.
Right, that's consistent with that too. Now we haven't tried to do something like make a model for their particular experiment and quantitatively, map.
But at least the trend is
right. Right, the trend is right. And in terms of things like Nyquist, where you're looking at like time dependence of all these behaviors, I guess you'd say that for all of the continuum models I've been working on, we've been in making a quasi-steady state assumption. So we haven't been looking at the time dependence. But in principle, one could, generalize these models and consider that as well. Which range the approximation? So for Sorry, can you say that again?
So I'm really real. How much?
You're asking what is the best you could hope to do given these models? So I guess it depends on which particular case you're looking at. So like, for example, in the case of the doping, in the doped lithium peroxide, the model predicts that with cobalt, the potentials associated with transport, the overpotentials, could be reduced to a few millivolts, which is much smaller than what they normally are, which is on the order of 1 volt. Does that answer your question? Huh? What would happen if there was other types of defects? You mean what is the maximum amount you could add? Oh, so okay, so in our model, we're assuming that the amount which is incorporated is given by equilibrium. If you have a lithium oxygen electrode which has excess cobalt oxide in it, or excess lithium cobalt oxide in it. So that represents the maximum which you could get. So in other words, you add excess cobalt to your electrode. So in other words, according to our model, you couldn't get any lower than those few millivolts because you can't get any more cobalt in there. It would precipitate out as lithium cobalt oxide. Does that answer your question? In the potential or in the concentration? Oh, so the concentrations of the cobalt here is about 1 part per million. So if you want to see what those equilibrium concentrations, so the lowest energy cobalt defect is this one right here, about 10 to the 17 per cubic centimeter. And so if you add any more than that, then the cobalt would precipitate out as lithium cobalt oxide.
So the lithium were the most common forms of effect.
Yeah, and the intrinsic.
So independent concentration effect, is there one particular defect or all at equal concentration that
Yeah, certainly. So if all the defects, okay, so the question is, if all the defects were at the same concentration, which one would have the most impact? And the answer presumably would be the one which has the highest mobility. And so we've only calculated, so there's a lot of like defects that are very high in energy, for which we didn't bother to calculate mobilities because we already know their concentrations are very low. But in principle, it could be possible that there's some very high energy defect that has a high mobility.
if there was one.
So is there any way you could, if there was a high energy defect?
Yeah, just make it higher.
I'm not sure how you could do that. Maybe if you had substantially changed the composition of the material, might be one way to do it.
That's what's happening here, right?
Right, right. But so even in the case of doping, you can certainly change the formation energies, but you still end up with the same intrinsic defects you had before. So if the lithium vacancies were the dominant defect in the intrinsic case, there's still the dominant defect in the extrinsic case. If you wanted some way to bring down some other type of defect, which normally would be even higher in energy, down to a lower energy, I don't know, I think it's an interesting question. I don't have a good answer. Well, so I think the easiest one to pursue is easiest one to pursue is, of course, adjusting the temperature, because experimentally that's the easiest knob to turn. In terms of which one is the most promising, I don't know. I think it's anyone's guess. I think that maybe creating an amorphous discharge product is the one that seems to be something that people have demonstrated can be controlled by some other factors, is introducing a certain catalyst. So I think maybe that might be a good one to explore.
Okay. Last call for questions. Okay. Well, thanks everyone. Grab some snacks on the way out. So